Hello, and thank you for taking a moment to view my video entitled Image Analysis Highlights, the Colorado Floods. My name is Joe Peters, and I'm a Solutions Engineer with Excelis Visual Information Solutions, located in Boulder, Colorado. In the fall of 2013, residents along the Front Range of Colorado experienced an historic storm event that caused widespread flooding throughout the region. During an 8-day stretch beginning September 8, 2013, and concluding September 16, 2013, the county of Boulder, Colorado, and the surrounding region received over 17 inches of rainfall. Due in large part to the steep topography and narrow canyons that comprise the western portion of Boulder County, this excessive amount of rainfall resulted in many localized flash flooding events that caused damage to roadways, bridges, and buildings, and caused many creeks throughout the region to create new channels and extend beyond the floodplains predicted by FEMA floodplain maps. In the wake of the flood, myself and several colleagues at Excelis Visual Information Solutions began working with satellite imagery from before and after the flood to see what information we could extract that would be of use to first responders, GIS analysts, and other stakeholders in this event. Following any natural disaster, imagery obtained from airborne and spaceborne sensors can play a unique role in the assessment of on-the-ground conditions by providing timely data over broad and inaccessible areas. This can lead to improved accuracy of GIS information. Additionally, image analysis tools such as those found in ENVI software can save time by providing automated methods for extracting important information. This is often accomplished by taking advantage of the full range of spectral properties provided by today's modern remote imaging sensors. In natural disaster situations, remote sensing plays a key role in a tiered assessment of damage. Beginning with Tier 1, change detection performed on moderate resolution imagery, such as imagery provided by Landsat ETM Plus and OLI sensors, can provide a quick look at the impact that a disaster has had on a region. Tier 2 assessment using high-resolution imagery, such as imagery provided by Worldview 2 from Digital Globe, can help pinpoint which communities in a region might be more seriously impacted by a natural disaster event. Finally, Tier 3 assessment can be conducted to determine damage to individual structures within a community. In this presentation, we will take a look at methods for conducting Tier 1 and Tier 2 assessments. For Tier 1 or regional assessment, we will use imagery obtained from the Landsat OLI sensor. This is freely available data provided by the United States Geological Survey's Earth Resources Observation and Science Center. Pre-flood Landsat 8 imagery was captured on June 6, 2013. Post-flood imagery was captured on September 17, 2013. For Tier 2, or neighborhood assessment, we will use imagery obtained from Worldview 2. This imagery was provided by Digital Globe. Pre-flood Worldview 2 imagery was obtained on September 12, 2010. Post-flood imagery was obtained on September 18, 2013. Satellite imagery used in this presentation was pre-processed using the radiometric calibration and atmospheric correction tools available in ENVI. Radiometric calibration attempts to compensate for radiometric errors from sensor defects, variations in scan angle, and system noise to produce an image that represents true spectral radiance at sensor. Atmospheric correction is a critical step when comparing two images of the same scene taken at different times, removing atmospheric interference to provide images that are more accurate and reliable for performing quantitative analysis. We will begin our analysis with the pre-flood and post-flood Landsat 8 images, which are visualized here using a SWIR1 green-blue band combination. This false color representation of our scene shows water in shades of blue. Note that the post-flood image contains considerably more light blue features than the pre-flood image. This is the floodwater that we wish to extract from the scene. An interesting side note, the post-flood image was captured the day after the storm event. This was somewhat a stroke of luck, as Landsat 8 has a revisit period for each scene of approximately every 16 days. This scene happened to be captured by Landsat 8 on the first cloud-free day after the storm occurred. The OLI sensor aboard Landsat 8 has 9 bands for capturing the spectral response of the Earth's surface at discrete wavelengths. The wavelengths of these bands have been chosen carefully based on years of scientific research. Landsat 8 was put into orbit on February 11, 2013, and represents the continuation of the Landsat program, which offers the longest continuous global record of the Earth's surface. There are several remote sensing methods that we could use to extract water features from the pre-flood and post-flood images. One method that I found worked quite well and was fairly easy to perform was the Modified Normalized Difference Water Index. This method takes advantage of Landsat 8's shortwave infrared 2 spectral band to extract water from the scene. The modified normalized difference water index is a modification of the normalized difference water index, which produces better results when monitoring open water as opposed to vegetation. Performing the modified normalized difference index on a Landsat image results in a grayscale image in which brighter pixels represent open water. After calculating the modified normalized difference water index for the pre-flood and post-flood Landsat 8 scenes, the Raster color slice tool in ENVI can be used to extract the pixels that depict water from the images. Raster color slices can be exported in multiple formats, including vector shapefiles. This is a quick and easy method for extracting features of interest from imagery for further use and manipulation in ArcMap. When information extracted from imagery is combined with traditional GIS data layers, we can begin to see important relationships and start to quantify some of our results. For this presentation, GIS data was obtained from Boulder County GIS, FEMA, and the USGS. In order to perform further analysis, vector shapefiles for pre-flood and post-flood water extents were sent to ArcMap using ENVI's unique one-click push interoperability feature that automatically sends data layers from ENVI to ArcMap. The total water area calculated from the Boulder County Lakes and Reservoirs data layer was approximately 26.5 square kilometers. The total water area extracted from the pre-flood Landsat 8 image was approximately 28.8 square kilometers. A visual inspection of the pre-flood image shows that the modified normalized difference water index was actually quite accurate and picked up several water bodies that were not included in the Boulder County GIS dataset. The total water area extracted from the post-flood Landsat 8 image jumped to approximately 56.9 square kilometers. A simple analysis model was built using ArcGIS Model Builder to compute where floodwaters intersected parcels, roadways, and railways. This model was built using a parameter so that a buffer distance could be added to the floodwater feature, which can be used to determine which features were within a specified distance of floodwaters. The thought here is that if a parcel, roadway, or railway is within a certain distance of floodwaters picked up from satellite imagery several days after peak flow, there's a good chance that the feature was affected by the flood. This could prove beneficial for workers trying to figure out where to start when performing post-flood inspections to determine the extent of damage to roadways, railways, and other features of interest. Results of running the GIS proximity analysis model show that of the approximately 90,000 residential parcels in the Boulder County GIS database, 4,231 intersected floodwaters extracted from remotely sensed imagery. Unfortunately, data does not yet exist to compare the analysis results to the true number of residences affected by the storm. What this analysis does offer is a good starting point for examining which residences may have been affected. We can also use the data that we extracted to see how well FEMA floodplain maps did at predicting the location of floodwaters. For this analysis, the total floodwater outside of the predicted FEMA 100-year floodplain boundary was approximately 13.8 square kilometers, while approximately 15.3 square kilometers were within the predicted 100-year floodplain. These results might appear a little bit deceptive, as much of the water outside of the FEMA 100-year floodplain is either surrounding reservoirs or in isolated areas such as open fields, rather than within the proximity of a specific water channel. Let's now move on and take a look at our Tier 2 or neighborhood assessment using high-resolution WorldView 2 imagery, which has been provided by Digital Globe. WorldView 2, launched in October 2009, is the first high-resolution 8-band multispectral commercial satellite. WorldView 2 provides 46 cm panchromatic resolution and 1.85 meter multispectral resolution. It has an average revisit time of 1.1 days and is capable of collecting up to 1 million square kilometers of 8-band imagery per day. A quick side-by-side comparison of Landsat 8 imagery at 30 meter spatial resolution and WorldView 2 imagery at approximately 2 meter spatial resolution shows how we can conduct a more focused study of damage caused by flooding on a neighborhood level using imagery obtained from WorldView 2. For the neighborhood assessment, we will take a look at the effects of landslides along a popular hiking trail in the surrounding neighborhood in Boulder, Colorado. The first step for this method was to delineate vegetation within the pre-flood and post-flood images. This was done by applying the normalized difference vegetation index to the scenes. The reasoning here was that if a pixel contained vegetation both before and after the flood event, then we can safely assume that it was not influenced by the landslides. The next step for this method was to perform a maximum likelihood supervised classification using the NDVI results to mask out areas of the image that were covered with vegetation. The maximum likelihood supervised classification used a user-provided region of interest to train the algorithm to pick out pixels from the scene that represent bare earth, dirt, and mud. In the images shown here, areas in yellow represent bare earth, dirt, and mud. After performing the image classification, a thematic change detection was applied to the before and after classification images to determine where bare earth and mud were present in the post-flood scene, but not in the pre-flood scene. This worked well to determine where landslides were located along the mountainous ridge along the western portion of the scene, as well as determining which roadways and lots within the neighborhood were affected. Further investigation for this type of study could employ other image analysis methods, such as image change detection and feature extraction using high-resolution imagery to begin looking at Tier 3 assessment. A comparison of pre-flood and post-flood LiDAR data would also be an excellent resource for looking at damage to individual structures and changes to elevation, and for calculating changes to the landscape brought about by the erosion and deposition of sediment caused by the flood event. SAR data could also be used to look at changes to the landscape in very fine detail. We are also beginning to see the emergence of UAVs to help with natural disaster response. If UAVs are utilized as part of a well-coordinated component of an emergency response plan, the data that they acquire may prove invaluable. In communicating with members of local GIS departments following this flood event, it became clear that the extent of flooding and broad regional scale of this disaster made it very difficult to respond to. Many members of local GIS departments were flood victims themselves. Both during and after the flood, many areas were simply inaccessible due to a variety of problems caused by floodwaters. The ability of remotely sensed data to see areas that might not be otherwise accessible makes it a highly valuable tool for responding to this type of disaster. While remotely sensed data will likely never fully replace traditional GIS data collection techniques, its use as a unique and necessary tool in obtaining geographic information should not be overlooked. Thank you for taking the time to view this video. If you have any questions or would like to talk to a representative, please contact us at info@excelisviz.com.